Hello everyone, I'm Larissa, and today I'm presenting Performance Detective, which is about deducing not only cheap but also accurate performance models. This is collaborative work together with Martin, Alexandru and Torsten from the ETH Zurich and also Andreas from the University of Applied Sciences Karlsruhe. To start off, the motivation for our work was the high cost of computing clusters. For example, this paper estimates 5.5 million euros of yearly operating cost of the cluster in Aachen. And this other paper predicts an energy bill of 10 million euros per year for an exascale system with their, at this time, very optimistic estimate of 20 megawatt, which now turns out to be quite realistic now that Frontier has been announced with 21 megawatt of power. And looking at the rising energy prices, the energy bill produced by Frontier may be even higher than the 10 million euros per year that they predicted. So this, of course, means that application developers should make use of these resources in an efficient way and ensure that the applications scale well. However, that can be hard due to the influences of configuration options. And it's not only individual configuration options that impact performance, but also combinations of them. And an example of a combination of them is the scalability challenge. Which means the interaction between the number of processors and the problem size that you use. And to illustrate this, we have here, for example, various options that influence the performance, where you can set a value of 1 to n for each of them, and then they result in some performance value. And usually it's the runtime that is of interest here. And of course, now the question arises, how can we choose the best configuration with the lowest runtime? This is where performance models come into play and can help in understanding the application behavior. For example, here on the right side, we have two performance models for the functions step 1 and step 2, where they explain how the configuration options on the left impact the performance. While these performance models can be generated analytically, there's also automatic performance modeling, which does not require a performance expert, but just generates models from empirical measurements. However, of course, we now need a smart strategy to use to select the configurations we want to measure. Because, as you can see, the configuration spaces are quite big and exhaustive measuring is, of course, unfeasible in that. So there are existing workflows to tackle this problem, and I would like to introduce two of you to you, which is XtraP and also a performance influence modeling workflow presented by Weber et al. And usually they consist of a 4-step process, where in the first step the system is analyzed and parameters to be modeled are picked out. In the second step, it's decided about an experiment design, so which points we should measure to create the performance model from. In the third step, the experiments are actually executed, and in the last step, the models are generated from the measurements. So for XtraP, in the first step, an expert selects the parameters to be modeled, and they propose to use a full-factorial measurement design using 5 values per parameter. They instrument all of the functions for the instrumented experiments, and then model all functions, including potentially noise, as they do not know which parameters the functions really depend on. For Weber et al., they start off in the same way. An expert selects the parameters. However, they use a different approach to this sampling, where they use a Placker-Berman design, where you decide about how many measurements you want to take, and also how many values per parameter you want to have, initialize that with a random seed, and then end up with the measurements you have to take. For the experiments, they use a 2-step process, where they first sample all functions and try to learn models for them. And in case they cannot learn an accurate model, they trace these functions to learn more accurate models of them. And their modeling method is decision trees, also potentially including noise, as they have no knowledge about the real dependencies from parameter to performance. So there's also a more white box approach to performance modeling with XtraP, which relies on Perf-Taint, which is a system analysis that produces a parametric performance profile of the application, saying how input parameters impact the performance of each function. However, they do not make use of this for the experiment design, but still propose to use a full factorial measurement design. However, in the third step, they then can go ahead and instrument only the functions identified as relevant by Perf-Taint, and also model only the relevant functions based on the known dependencies. So, and this is where our workflow comes into play. We also use the parametric performance profile provided by Perf-Taint. However, in the second step, we then make use of this to deterministically reduce the experiment design with performance detective. And then in the third step, we also instrument only the relevant functions. However, for modeling, the approach is orthogonal to the modeling approach used, and we will show how to use the modeling together with XRP and also with performance influence modeling. So, as I said, the contribution is that we show how to come up with a minimal experiment design, and I will now show you how we go about this. First, by introducing the system analysis we use, which is Perf-Taint, by a simple example program. So here on the left, you can see the main routine of the program, where the input parameters are read in, which are x1, x2, and iter's. Variables are assigned, and then the first main computation routine foo is called, where foo first iterates over iter's, then over y, calls bar later on, which itself iterates over z, and then calls precalculate. And now the system analysis already tells us that the time of foo will depend on the input values of x1 and iter's, the time of bar will depend on x2 and iter's, and that the time of precalculate is assumed to be constant because there is no loop in it, which depends on the input parameters. So what we can also see is that iter's linearly influences the runtime of the main computation as it is the outermost loop, and also that there is no function that depends on x1 and x2. And now we will make use of these insights for the experiment design. So from the full factorial standpoint, we would start off with the experiment design space consisting of 3 parameters, x1, x2, and iter's, resulting in 125 measurements. However, applying our first insight, which is that iter's influences the computations linearly, we can strike out iter's as a parameter, giving us only 25 measurement points measuring combinations of x1 and x2. Now, applying our second insight that there is no function that depends on both x1 and x2, we already know that there will be no interaction between x1 and x2. So we can also strike out measurement points aimed at finding interaction between them, leaving us with only 5 measurement points compared to 125 we would have started off with. Now, for the instrumented experiments, we can again make use of the knowledge that iter's influences the computations linearly by skipping the repeated measurements. So approaches until now suggested to repeat each measurement 5 times. However, we do not need to do this if we can already be sure that the main calculation will be executed often enough, which means in this case setting a value of iter's to 5 or higher. This will of course not shorten the time needed for the main calculation. However, this saves us the initialization overhead of the application. As I already said, the usage of performance detective is orthogonal to the instrumentation and the learning methodology used, so we will also evaluate modeling with 2 different approaches, which are XRP and the performance influence models, where the XRP approach we will compare against a full factorial sampling and also the sparse sampling design, where they only take 5 values per parameter and 1 point of interaction between them. For both sampling designs, they use the regression to the so-called performance model normal form as learning method. And for the performance influence models, they use a Plackett-Berman sampling design, as explained earlier, and decision trees as a learning method. For the evaluation, we evaluated 2 applications, which are Kripke, a 3D as a particle transport application, and Pay3D, which is a multi-physics solver. And I will now tell you more about this. So Pay3D in general simulates how a material reacts to certain outside influences. And in our case, we picked the pressure calculation with a projected conjugate gradient method, which has 4 parameters, which are the number of processes to use, the volume of the total material, then the spacing on the coarse grid, which is laid over the total material to first calculate some approximate solution there, and also the number of iterations of the solver. And the results of the system analysis are shown on the right, where we can see that while there are various interactions between parameters, between vol and cubes, there is none. So there's no function that is influenced by both vol and cubes. And again, we will make use of this, as in the example I showed earlier. So from the black box standpoint, we would start off with 4 parameters, which I explained earlier, and 5 repetitions per experiment, resulting in 3,125 experiment executions. Now, applying our first insight that again iter's influences the computations linearly, we can strike it out as a parameter and now only have vol, cubes, and procs left as parameters. And also we can skip the measurement repetitions and instead set iters to a value equal or higher than 5. Now, applying our second insight that vol and cubes actually do not interact, we can also strike out measurement points aimed at finding interactions between them, leaving us with only 25 experiment executions, compared to 3,125 we started off with. So that's only 4% of the samples needed previously. And now we will evaluate whether it was indeed a good idea to use only this few samples. First, by evaluating how modeling using only a single repetition of experiment works like. So using the traditional sampling design. And I will start off with XRP and 5 repetitions, where we can see that for Pay3D, the error is around 8% for interpolated measurement set and around 9% for the extrapolated test set. And now if we compare this to the models generated from only 1 repetition, we can see that the errors are indeed around the same. The same is true for Kripke, where with 5 repetitions we have a prediction error of around 4 and 18%, which stays around the same if we only use 1 repetition. For performance influence models, we have a generally higher error of 20% for the interpolated test set and 60% for the extrapolated test set. However, using only 1 repetition doesn't change much about this. And the same is true for the Kripke application, where we have around 21 and 25% errors, which again are around the same if we use only 1 repetition. So this step seems to work, and I will now continue with the models learned with only 1 repetition for the performance detective, and also now compare the actual experiment design we deduced, striking out all the measurement points. Where I would first like to compare against the full-factorial measurement design, both learned with and without the use of Perf-Taint. And first we can see for the core hours that performance detective only needs around 11 core hours, whereas the full-factorial measurement design is much more expensive, needing 368 core hours. So performance detective gives us a prediction error of around 8% for the interpolated test set, and also around 8, maybe more 9% for the extrapolated test set. And the full-factorial measurement design, however, gives us around the same errors with 9 and 10 respectively, and a bit lower errors for the full-factorial measurement design without Perf-Taint, but still around the same. So compared against the sparse modeler, where we only use 5 values per parameter and 1 point of interaction, we can see that for this case study, the usage of the sparse modeler is even less expensive than the usage of the experiment design deduced by performance detective. However, looking at the errors, we can see that the error of the sparse modeler is a lot higher for the extrapolated test set, around 17%, and without the use of Perf-Taint, the sparse modeler even has an error of around 30% for the extrapolated test set. which is quite high. So compared to the modeling with the decision trees and the Plackett-Berman sampling design, we can again see that the use of performance detective is much cheaper than the Plackett-Berman design. So the errors we get with learning models using decision trees with the performance detective experiment design are around 20% for the interpolated test set and around 47% for the extrapolated test set, which again is a bit higher than the XRP modeling. However, if we use the Plackett-Berman sampling design, we can see that they are around the same, and so the use of the performance detective experiment design still provides the same accuracy as the much more expensive Plackett-Berman sampling design. So to conclude, the problem is that performance modeling workflows use heuristic sampling, and our contribution to this is that we show how to deduce a minimal necessary experiment design based on the insights by the system analysis. And our evaluation on 2 applications showed that we can maintain the model accuracy while significantly reducing the needed core hours. Thank you for your attention today.